Okay, this is part 2, but I'm going to assume that you forgot a few things. Not going to remember everything, but the essential parts that we need. Um, this is joint work with Eduardo Dueñez, um, Jose Llovino, Donna Matos, and Frank Toll. Okay, so let's recall the following, which will be the object of study today. A compositional computation structure or CCS is a triple L, E, and gamma, where L can be embedded in the product of R to the P, and this is a topological space, and gamma is a semigroup of maps from L to L, semigroup under composition. Okay. Few names. So L is known as the space of states. E is a collection of predicates, or also called features. Features or predicates, if you like, first order terminology. They're essentially measuring attributes of each state, and each of them are going to be real valued. Okay. What else? So gamma is the space of computations. Okay, and computations are going to be maps that transform one state into another. Calligraphic L is going to denote the closure of L under this space with the topology of pointwise convergence. This is the space. This is called the space of type states. You can think this has limit states or ultra limit states, which are going to represent, well, the limit points of states. And last one, elements in the closure, or I think better say this, for any set of computations, not necessarily a semigroup, the closure is a space of deep computations. Okay, this closure is a subset of. So this closure is a subset of the calligraphic L from L to calligraphic L. Okay, right. So what else do we need? Okay, that's it. So the point of the talk is to analyze how the topology of this space says.
The delta bar is not the closure.
Sorry?
The delta bar is not.
Is the closure. Is the closure under has a subspace of L to the L with the pointwise. Yeah. The closure L bar. Yeah. Okay, so the point of the talk and this work is to analyze the relationship between the topology of this space of deep computations and notions of learnability in the computational context. So to state the main theorem, we need
trying to get information about computability or computations
from the
by
topology.
looking at the asymptotic limit.
Right. Yeah. One of the typical questions, because it's supposed to be in the applied scenario, is that you want the deep computations to be sequential limits so that you can approximate with a sequence of computations. And we are going to provide conditions for which this is true. That's one of the consequences of the main theorem. Okay, so a few other things I need to define or remind you. Given a sizer, so let's remember a sizer is just a tuple indexed by the features or predicates. The purpose of a sizer, as the name indicates, is to assign upper bounds, assign bounds to each feature of states. For computational reasons, this is important. So giving a sizer like this, we define the shard, which is the set of all states where the p feature of the state is bounded by Rp. This is the R shard. So note that the shards cover the space L. Similarly, you can define the type shards, which are the same, but replace L by L bar. Okay, so ultra states where the features are bounded by whatever the sizer says. This is the type shard. Okay, and lastly, it is not true in general that if you take the union of the type shards, you recover the full space L. The space that you obtain is something that is potentially smaller. So we will denote it as LH, L shard, which is the union of all type shards. The comment here, this is an easy observation, is that if the set of features, which typically is going to be P, is countable, then so this is a subset, then these two sets are the same. This is true because P being countable will make this space R to the P a Polish space, particular Fréchet unison. So L is going to be also Fréchet unison. If you take any type state here, you can take a sequence that approximates this. The sequence and the point is a compact subset of R to the P, so it's bounded, it's pointwise bounded. And the pointwise bound tells you that it belongs to a shard. Okay. More definitions. Right. So
Shards divide the space into small compact pieces, which are easier to add.
right, exactly. Okay, so a collection of sizers. We are not working with every possible sizer. a collection of R of sizers is exhaustive if they cover the space. If the shards from the collection cover the space. And we say a set of computations delta is R confined if for every computation, when you restrict to the shard for any sizer in R, when you restrict the computation to the shard, the map preserves the bounds. So it sends states here to states in the same shard. Preserve the bounds. Okay, and the last ingredient that we need to state the main result is something that Tona started to mention last time, and maybe some more explanation needs to be done. So this is called the extendability axiom. We're going to assume that our CCS satisfies extendability axiom. Okay. So what does this say? It says that every computation can be extended to the shard space in such a way that the restriction to every shard, type shard, is continuous. So that for any sizer, the restriction is continuous. This implies in particular by compactness that the image, the range, is going to be contained in another shard. We don't know which one, but it's going to be contained in one for a different sizer. All right, so why is this axiom important or relevant in this context? Because in some way it is a definability axiom in the model theoretic sense, or a computability axiom if you prefer. So the reason is continuity on these compact sets allows you to uniformly approximate these maps with polynomials over the predicates. So predicates, you can view predicates as continuous maps, which are the projections from L to R. This is the algebra of polynomials is generated by these predicates, separate points. So by Stone-Weierstrass, you get uniform approximation. Let me be precise. So extendability axiom is equivalent.
So needs any hypothesis on L? Like, I mean, the L is empty or something.
Well, sure, non-empty. Yeah.
Non-empty, that's all.
You need no, because this space is compactness, and that's all you need. Compact Hausdorff, right? Sure, non-empty. Okay. So this is equivalent to the following. For any computation, for any sizer, for any feature, and any epsilon, you can find a map that depends on the sizer, p, and the epsilon. So this is definable. Moreover, we can take this to be a polynomial. So this is really a computability polynomial over set of predicates such that for any state, so this approximates the feature of the computation. Up to epsilon, of course.
Philip's question, though, I mean, you do need something to apply the Weierstrass theorem. You need some algebra where you
Right.
can add, so that has to be included here.
Right. So we're applying some bias stress to the set of, okay, so you fix the predicate, right? So this is a continuous map from the compact space to R, real valued. And inside there, you have an algebra that is generated by the features P, the predicates P. Predicates are maps. You can think predicates as continuous maps. Or the projections.
Right. But nowhere does it say that you have an algebra of maps. I mean, these might be just random maps, but no connection between them.
So you have polynomials over P. That's going to be generate an algebra. Yeah.
Include all of those.
Right.
Part of your, okay.
Generated by P.
So it's
yeah.
not just an.
No. Right. Polynomials.
Polynomials or other things that you're going to say are true.
Right. Polynomials is important for obvious computability assumptions. Okay, so extendability axiom is really definability axiom if you like model theory, computability axiom if you like computability.
I'm sorry, even if you have polynomials, I mean, you still need to be able to add them and so on.
Yes.
Right.
Okay.
Yeah. Yeah. So that's, you use the algebraic operations.
Okay.
Has a ring. Okay, right. Ring of continuous functions.
Yeah.
So trying to convince us that it's plausible to assume this.
Yeah. Well, this is the reason. This is the reason, right? Okay. Forgot to mention something why this is important. The R confined. This is another observation that is not difficult to see. Is that the confinedness, if delta is R confined, then the set of deep computations is a compact set. Is compact. All right. And now, now I guess I get to state the main theorem. Right, doing well.
Computation itself continuous?
Sorry?
Is every computation gamma itself?
Not necessarily, but it has to be continuous on charts, type charts. I'm going to give an example where this is some examples where this is noticeable. Okay. Yeah, so in particular, it's going to be continuous on these charts. Okay. Let L P gamma be a CCS satisfying the extendability axiom. Let delta be a set of computations, which is R confined for some exhaustive collection of R upsizers. The following are equivalent. Okay. So one, for any sizer, the set of deep computations restricted to the shard. Okay, some notation, I guess. We denote by gamma tilde to be the set of all extensions. Okay, so we're taking limit points of this set restricted to the shard. So this is a set of Baire class 1 functions from the shard to the shard. This is R confined.
Gamma tilde. So are you picking a sort of
Yeah.
favored extension?
Yes, right.
Okay, so you're choosing an extension.
You're choosing an extension, right? Yes.
You're not just taking all of them.
No, no. Yeah. One for each. Yeah, thank you. That's a good point. Okay, so deep computations are Baire class 1. If and only if the following happens, this is the non-independence property analog of this in this case. So for every R, for any P, and for any countable set, I forgot one assumption I'm going to clarify in a moment. Any countable set of computations and any two real numbers, we can find finite disjoint sets. These are finite and disjoint, such that there is no X in the L shard with the property that the P feature of the nth computation is below A for all n in one of the finite sets, and all the features of the nth computation are above B for n in the other finite set. Okay. The assumption that I missed is that we need to assume P is countable for this. Okay, let me check that I didn't miss any assumptions here. Okay, yeah, it's correct. In particular, every deep computation is Baire 1 definable in the sense of the extension. So you replace continuous by Baire 1.
Actually, do you want a tilde on your gamma there?
Here? Oh, here, yes. Thank you. Typo. Right.
So in here, you're assuming these things are confined?
Yes. Are
Oh, there it
confined.
is, okay.
Yeah. And every deep computation is Baire 1 definable, so it means the asymptotic behavior, the asymptotic computations that you get in the limit are nice, are as close as continuous as you can be, or very close to continuous, maybe not as close to continuous. And our every deep computation and is a sequential limit of computation. Is a sequential limit of computations in delta. Okay, this first part follows from number 1. The sequential limit follows because, and this is where we use countability. well, we use countability in this equivalence as well, but also Bear class 1, this is a Rosenthal compactum. So this is, you can think this space has homeomorphic to, or embedded in the product of P with the compact set, compact Polish, real valued. This is a Polish space as well. If you give P the discrete topology, of course. So this is a Rosenthal compactor, and one of the main properties that was shown in the work of Bourgain, Fremling, and Talleyrand is that Rosenthal compacta are, or that this space is Fréchet Urysohn. So limits are sequential limits. That's why this follows. Okay, so few remarks on the proof. The proof is not, even though this is a result about deep computations, it's not a deep proof. It really follows from, this really follows from Bourgain, Fremling, Talleyrand. The similar equivalence that Tana presented last time. So what are the differences? You're not R valued anymore. You are R to the P value, but that's easy fixable. You need to consider also for all P, but that's fine. The other difference is that you have finite is shown here. In BFT, you have a set and its complement, but that's a compactness argument. And here, you should have the same space here. The reason why we can go from here to the closure and vice versa is because this property NIP holds for a set if and only if holds for the closure. Also not. So it's not a proof that I think I should spend much time explaining, but the important things are the consequences of this. Any questions? Okay, so this theorem, the point is, this theorem gives an equivalence between a topological condition and a very computable condition. So we can use topology, what we know about Rosenthal compacta, to say a few things about this type of computations. Here's one thing. Rosenthal compacta, there are many examples that were studied in the literature, in particular by Todorchevich in his 1999 paper called Compact Subsets of the First Baer Class. So let me begin by defining a few things. So under assumptions of the previous theorem, we say that a set of computations is NIP if and only if it satisfies 2, equivalently 1. We are going to subclassify these NIP. So the picture that you can have in mind, so is this. Here you have the stable case. So stable in this context means that the set of deep computations on the charts are continuous. So deep computations can be also extended by continuous functions. This is the case where everyone wants to be, because then you can uniformly approximate your deep computations by polynomial. Same reasoning. However, it's not going to happen all the time. And here you have NIP. I'm ignoring what happens outside, the other unstable case. What we are going to do is we're going to subclassify this area of NIP by analyzing topological properties of this of the closure of this set. So we're going to have, I'm going to explain what these are. So this NIP, NIP1 is going to be a subset of NIP, NIP2, subset of NIP1, and NIP3. So what are these NIPIs? Okay, so we say that set of computations is NIP1 if the Rosenthal compactum I guess I mean for all sizers. So the Rosenthal compactum is first countable for all R. We say it's NIP2 if the Rosenthal compactum is hereditarily separable for all R. And NIP3 if the space is metrizable. For all sizers. Okay. Note that NIP3 implies NIP2 because this is a compact metrizable space. NIP2 implies NIP1 because this is a Rosenthal compact. This is a result from Roman Paul. Every Rosenthal compactum that is hereditarily separable is first countable. And then the rest. And the following trichotomy, if you prefer, which is part of the work of Todorchevich, Argyros, Dodos, and Kanellopoulos, say that they're essentially, these are the only spaces, interesting spaces you can get. Let me explain what that result is. So this is the theorem by Todorchevich, and later, so a version of this result was given in the 99 paper, and then 9 years later, Argyros, Dodos, and Kanellopoulos let me check the spelling there. That's right. From 2008, extended some of Todorchevich's result to obtain the following trichotomy. Suppose that K is separable Rosenthal compactum. By the way, we are going to assume from now on that the set of computations is countable. So these are not only Rosenthal compactable or separable Rosenthal compactum. Okay, so two things can happen. Either K is metrizable, or is not. Okay, I'm getting somewhere. In the case where you're not metrizable, two things can happen. Going to need more space here. two things can happen. Either you are hereditarily separable, or you're not. In this case, meaning when you are when the space is non-metrizable but is hereditarily separable, then a typical space, the double arrow space or the split Cantor, embeds in K. This is witness of the failure of non-metrizability, but hereditarily separable. And lastly, either you are first countable or not. Not. So in this case, there is another space that embeds in a very canonical way, which is called the Alexandrov duplicate. I can explain what this is in a moment. Or the one-point compactification of a discrete space of size continuum embeds K, this case. So these are the three interesting spaces for Rosenthal compacta. And it is possible to consider CCS where the different examples of CCS where the closures are exactly these spaces. Well, not okay. This is not separable, so you have to actually look at separable. You can add countably many points to make it separable, and same here. But you can find a copy of the non-separable versions inside the space of deep computations. Okay. Okay. Should I do? Okay, I guess let me show you examples. Any questions so far? Okay.
So Stavo's result, if I remember correctly, is more general, right? Because it's about the existence of a dense metrizable subspace.
That's one of the results. That's the first lemma in the paper.
Right, but it doesn't. I don't think you have to assume separable.
If you don't assume separable, you can still find embeddings, but in the separable case, you have either this happens or this happens or this happens. So Stavo defines in that paper what is called premetric compacting of degree 2. That's the condition that allows you to say if you are either you are this or you contain an uncountable discrete space. And right, yeah. So it's it's a more general result. Yeah.
Yeah, no, certainly prove things for non-separable groups.
Yeah.
You don't have as nice a hierarchy.
Right. Okay. We are doing well on time. Okay, examples. Computation of square roots. Of square roots. No. using Newton's method. Okay. So what is the problem? You have positive number, you want to estimate the square root. So you consider polynomial x squared minus a. Roots of the polynomial are going to be the roots. So you apply Newton's method to this polynomial. Newton's map is given by this expression, which simplifies to, okay, okay, simplifies to this. And then you iterate. So this n superscript means what you think it means. Compose this map n times. This can be framed in the has a CCS. So what is a set of state, the sets for which this function is defined. So all real numbers except 0. What are the predicates? So we want to extend these. The problem is that when you try to extend this map at 0, you get infinity. So we're going to embed this into the unit circle by stereographic projection. It's going to contain two features where the map sending x to p1x, p2x is the stereographic projection from R to S1 unit circle. So basically, for any state, you can measure the coordinates under that map. And the set of computations are the iterations of Newton's method. Okay. So we view L as the subspace of S1 by this embedding. It satisfies the extendability axiom because for 0 and the North Pole, you define the map to be the North Pole, the point at infinity. That is continuous. Only one sizer needs to be considered because this is already bounded by right. Everything is bounded by 1. Okay. Let's analyze the space of deep computations. It's going to be very simple. And the examples here presented are as simple as possible. Simple as possible. And then we can see in which of those hierarchies of NIP this belongs to. Okay, do you want to take a guess? Is it the stable, the 3, the 2, the 1? Okay, let's see. There is only one limit point, which is when you take the limit. So consider the limit as n goes to infinity of this map. So Newton's method in this particular case, and that's why we chose this example to present here, is going to converge to the positive root if your initial guess is positive. So X represents the initial guess, your initial guess, and then you apply iterate, and this is supposed to converge to the actual root. And it's going to converge to the negative one if your initial guess is negative. This cannot be extended in a continuous way. But it can be extended as a bare one function if you define infinity in the cases where you have the Newton's not defined. Right. And this is the only, right. So the set of computations is really this countable set with its limit point. This is metrizable. Metrizable. So it's NIP3. But it is not stable. Right. Okay, second example is important in machine learning. Okay, so second example. Yes.
It is distant, right? So you mean unstable. NIP3 but unstable.
Right, yes, yes. Right, thank you, thank you. It's not stable. Thank you. All right. Second example is called threshold classifiers. So these are going to be maps where if certain condition happens, it's going to be 0, it's not going to be active. When something happens, it's going to activate. So it's actually a discrete example. How this is framed in the CCS context, our space of states is the Cantor space. Infinite binary sequences. The features are measuring what is the end fit for the infinite sequence. So these are the projections. And for any finite binary sequence, we define the following map. It is going to be 1 if the first s bits of x are lexicographically below the finite s, and 0 otherwise. Because s is finite, this is continuous. Okay, I need a transformation. I need to transfer a state to another state. So you choose two states: the state that is always 0 or the state that is always 1. These are going to be maps continuous. And in this case, L is already closed, so make it easier. Okay, so the set of computations we're going to consider are the set of all these maps, are countably many, together with two constant maps. The map that is always constantly equal to the 0 sequence, and the map that is constantly equal to the 1 sequence. It is redundant that I write this because for this map is one of these form, but I'll just keep it there. All right. What is the closure? The closure, ignoring this, of course. You are going to approximate characteristic functions of things below a certain infinite sequence. It's going to contain maps for each infinite binary sequence. The map defined in a similar way. So is 1 if x is lexicographically below a, and 0 otherwise. But you also obtain other maps. You obtain maps where you have the strict inequality here, which we call F minus. Otherwise, you also have sorts of maps. This space is homeomorphic to the double arrow space or the split Cantor. So what is this? This is take the product of take two copies of the Cantor space, order lexicographically. So points, I'll continue Continue over there. So the double R space looks like this. You have two copies of the Cantor space. So the homeomorphism is given by points F plus represents points in the upper part, and the F minus represent points in the lower part. Okay, so this example is NIP2. So this is NIP2, hereditarily separable, but it's not metrizable. Okay, last example. The other not so complicated example that I can present is the following. You can call this the prefix. So it's another type of classifier. Same space, same list of predicates, and now for any finite sequence, you consider characteristic function of the basic open sets. It's going to be 1 if x and extends S, 0 otherwise. You consider the set of all these computations. And the deep computations are going to be, they're not in the set delta, are going to be delta maps. So characteristic of singleton points. Right. So if x is A otherwise, and also you obtain the zero map, which is homeomorphic to the 1-point compactification of a discrete space of size C. So this is an example which is NIP. This is still Rosenthal compactum, but it's not first countable. It's not NIP 1. All right. The other example separating these two is a bit more complicated. I'll leave it for maybe, I don't know when. You can ask me if you're interested. All right. Oh, one important thing that I should mention here is that NIP, as Tona mentioned the other day, is equivalent to having VC dimension in the discrete case. These are discrete examples. These are two-valued functions. You can compute the VC dimension in these cases, and you also obtain the VC dimension also measures that this space is more complicated. VC dimension of this space is 1. You can shatter 1 point, but you cannot shatter 2 points. In this case, VC dimension is 2. In the previous picture, which I can repeat, you have stable, you have NIP3, NIP2, NIP1, NIP. Here you have the first example, and here you have the second example. The third example is not going to be 2 values, it's going to be 3 valued. So what this shows is that the VC dimension does not cannot compare the space that is here, cannot be compared with the other two, but topologically they can be classified. This is the space that I'm not explaining in detail, but there is a space more complicated to describe. The important thing is that you don't look at VC dimension anymore. You have other tools to measure complexity. All right. Oof.
Are you claiming that the NIPs allow you to bound the VC dimension, or?
No, so you can also do the same picture with VC dimension. So NAP means finite VC dimension. But what I'm saying is that this is in the context where you have two-value logic, 0, 1 logic. The context here is real value logic, so more things are going to appear. Okay. Okay. Let me jump to another important part of the talk. This is a different section. It is called randomized NIP and Monte Carlo computability. Okay, I'm going to make the promise that there's going to be a set theoretic question at the end about a consistency result that we don't know if it can be shown in CFC. Okay, so what is Monte Carlo method? It's a method to solve deterministic problems using probabilities. So let's say that the answer to a problem that you are solving is the expected value of a random variable with some distribution. What you can do is you can take a large sample of points and use the empirical measures as approximations to the real average, the real mean. By law of large numbers, this allows this method to work very efficiently and is very well known in the computability context. So we are going to relate the NIP with these sort of computation problems. First, a few definitions. I think I need. Okay, universally measurable functions, which some of you maybe know, given Hausdorff space, and measurable space. We say that a map F from X to Y is universally measurable if and only if for every measurable subset of Y for every radon measure on X, the inverse of E is measurable with respect to this measure. Right? I can recall in words what Borel measure is. It's a Borel measure that is irregular with respect to compact sets. So measure of a set can be approximated by compact subsets and is locally finite, meaning that every point has an open neighborhood with finite measure. Consequence of this is that Radon measures on compact sets are finite, and finite measures are equivalent to probability measures. And this is what what we are interested in. So the remark here is that if X is compact, we can replace in the previous definition Radan measure by Radan probability measure. Probability measure. All right. Another things. Typically, we're going to look at the case where the codomains are. In this case, we take the Borel sigma algebra. And also, we're going to have products of the real line, potentially uncountable. So we're going to drop the countability assumption of P in this section. There are two natural sigma algebras you can consider here. You can either take Borel sigma algebra of the full space, or you can take the sigma algebra generated by subbasic open sets. These are not the same. So the one we're choosing is the smaller one, which is called the cylinder sigma algebra. So this is the sigma algebra generated by subbasic open sets. This algebra in the countable case is going to be the Borel sigma algebra if P is countable, but in general, it's not going to be. Okay. And the other comment. Right. So the other reason why we consider this sigma algebra is because a map from X to R to the P is measurable with respect to any measurable space, if and only if when you use this cylinder algebra, if and only if the measurability happens for every feature. So for every P, the feature of the computation is measurable. Okay. And the other thing is why universally measurable? So the reason is you want to be able to talk about okay, in order to use the Monte Carlo method, you need some assumptions, but at the very least, the computation has to be measurable with respect to the probability distribution you're using in your problem. So we're requiring that no matter which one you use, the function is going to be measurable. You can do things there. The other reason, we're going to see why in a minute. Another important thing about measurable functions, maybe that I should mention, maybe I'm not going to write, but I'm going to tell. Lucin's theorem says, I mean, in some sense, that measurable functions are almost continuous, right? That if you have a measurable function, you can for any epsilon, you can find a subset whose complement has measure less than epsilon, and on that set, on the other big set, the function is continuous. So measurable is stable in a different sense. It's almost continuous. And of course, if P is countable, every Berg class 1 function is universally measurable. All right. Okay. So a little bit of notation here. We denote by m x mu the set of all is the set of all mu measurable functions. Real valued. And mrx, this is notation by Bourgain-Fremling-Talleyrand, is the set of all universally measurable. Again, real valued. So this is a smaller set, of course. Okay, so what is the theorem here? Let L P gamma be a CCS, satisfying the extendability axiom. Let R be an exhaustive collection of sizers. Let delta be R confined set of computations, and that's it. Then the following are equivalent. Well, no, the following are equivalent, no. If delta has NIP, as in the previous theorem that I raised, then every deep computation is universally measurable. When P is countable, this follows from the previous case. But this is also true even when P is uncountable. And the proof relies on the following result. The proof relies on the following result, also by Bourgain, Fremling, and Talleyrand. It's a characterization of the NIP property, the same one that we used, but using measures or spaces of measurable functions. Okay, this is 78. Let X be Hausdorff space, and A a set of continuous functions real valued over X, pointwise bounded. The following are equivalent. 1, A is relatively compact in the space of universally measurable functions. 2, for every K compact, for any countable sequence in A, for any A less than B, you can find a set such that there is no X in X with a property that Fn of X is below A for n in I, and at the same time, Fn of X is above B for n in the complement. And the third condition is for every radon measure, for every radon measure, A is countably relatively compact in the space of measurable functions, mu measurable functions. So every infinite set has a limit point here.
Relatively countably compact from countably.
Yes, you're right. Relatively countably compact. Okay. So again, the proof is not complicated, and I better use the last 20 minutes to go over another notion closely related to NIP, which is strengthening, is like an intermediate between the stable case and the NIP case, and is very, very important for the Monte Carlo method in particular, and the theory of BC theory. Okay, so this is a concept that was introduced by Talleyrand in the year 84, while he was studying something called Petty's integration. So here is the definition. I need to look at this because I might get something wrong. Okay. Okay, so let X be a compact space. And mu a random probability measure. On X. Let A be a set of measurable functions, mu measurable functions, be countable and pointwise bounded. Then we say that set of functions is Talleyrand stable if there is no positive measurable set, and there is no two pair of real numbers A and B, such that for every n and almost all n tuples, the following is true: that every subset of n points is shattered. So for any I subset of 1 to n, you can find a function that witness f of wi is below a for I in I, and the other ones are above b. I not in I. Okay. Right. Why is this important? It's because of the following characterization that Talleyrand realized a few years later, and has to do with the Klivenko-Cantelli classes. Okay. No. Right. It is relevant in this context because of the following theorem. By the way, this is closely related. The way this is presented is very closely related to NIP. You can also call this like almost NIP, or right? Almost NIP. Okay. The result is the following. If you have a set of measurable functions, which is uniformly bounded and countable, and mu is a complete random probability measure. Complete means that every null set is measurable. The following are equivalent. Set is Talagrand stable. If and only if it is a Glivenko-Cantelli class. So let me write, this is a resulting probability. So let me write the result and explain what that means. Right. I never thought I would write an integral in the set theory seminar. Okay. This limit is 0 for almost all infinite tuples. So what this is saying is that you can approximate the average using empirical averages, which is what is really needed so that Monte Carlo works very, very nice. The picture that we have here is going to be a bit different than this one. Yes. Yes. Right. Thank you. Right. So that the empirical values converge to the expected value uniformly. That's important. Uniformly. It's like a notion of, it's like a version of the law of large numbers. Okay. These classes of functions are important in the theory of BCE. Vapnik-Chervonenkiv's theory for machine learning. So let me show you what is happening here. So remember, we have the stable case, which is deep computations are continuous. So they're nicely approximated. You also have the NIP. Talagrand stability is going to be here. Meaning maybe you're not stable, but you can do many random algorithms in your problem. So this is, okay, these are not the same. However, we don't know if these two are the same. We don't know if Talagrand stable is the same as NIP. So let me say consistently they are. Consistently they are. Also by Talagrand, I think this is 84. Okay, if you assume that interval 0, 1 is not the union of less than C many closed null sets. For example, CH implies this. If this is true, then Talagrand stable and NIP are the same. The way this is stated is that the closure is contained here if and only if A is Talagrand stable. Oh, oops. I think measurable functions, measurable real value functions over the measure mu.
Which measure?
You fix, okay. Fix measure mu on X, which is complete. You don't need complete here. Radon, any radon measure. On, oh, okay. Yes. 0, 1. Thank you. Here I actually mean universally universal Talagrand stable, meaning it is Talagrand stable for every measure. I think I forgot. Right, this depends on the measure, right? Is mu is Talagrand stable with respect to this measure? If that happens, universal Talagrand stability means you are Talagrand stable for every Rodin probability measure. All right, so consistently, and this is, okay, so this implies, this is mu. This implies that universally Talagrand stable is the same as NIP. But we don't know how to remove the CH, this problem.
Much weaker than CH.
Yeah, much weaker, yeah. We don't know how to remove this assumption. The other interesting result that I want to mention is that the negation of
So
this,
what
yeah.
It follows from that assumption.
Sorry?
Is it the middle line that follows from not being covered by less than C closed null sets?
What middle line?
Well, okay, so you've got.
Okay, this implies this is okay. This is a corollary.
So the theorem under the hypothesis is that if and only if statement.
Yes.
I see, that requires the hypothesis.
That requires.
Okay.
In fact,
Only one direction.
yes, exactly. That's what I was going to say. This is the direction that you want. Right. That NIP implies right.
Corollary also requires the same hypothesis.
Yes. We're working on right. We're working on the interval 0, 1. Radon measures. Yeah, so exactly under the same assumption. You mean yes. Okay, but the implication is also for a fixed measure, in particular for Lebesgue measure. This implication is also consistently false. That is known. This is a result by Bremling and Schella in the 90s. '93. So it says the following. It is I'm not going to describe the forcing. It is one of those complicated forcing notions that are built for these types of problems dealing with measures. So it is consistent with CFC that there exists a countable set of Lebesgue measurable functions on the interval 0, 1. So this is countable. This is Lebesgue measure. Pointwise bounded. Such that it is relatively compact in the space of Lebesgue measurable functions, but it's not Talagrand stable with respect to Lebesgue measure. So the question that we are interested in is
Put universal.
why not putting universally there?
No, I mean, okay.
Yeah,
Go on.
yeah. So the question is on that direction. So we want not only a set of measurable functions, we really want continuous functions. That's our assumption from the beginning. So the question is, suppose that I'm going to frame this in a, not in the computational way, but more perhaps a theoretic. Suppose that this is true with X compact. In fact, 0, 1, if you prefer, is countable pointwise bounded. Such that is relatively compact in the space of universally measurable functions, or in other words, satisfies the NIP. Is a universally Talagrand stable. So in other words, can you remove this assumption? The same question as before. Can you remove this assumption to get, but not to get this, to get this equality here? Other open, well, there are many more things that needs to be done. So in the first part, I talk about NIP1, NIP2, NIP3. One of the questions for further research is, can you characterize these notions in a non-topological way? The only tool that we have so far to identify these classes is topology. Can you do that in a combinatorial or computational way? The next step is to move to, instead of real valued computation, Banach value computations. There is a need to get closer to the non-commutative case or the quantum case. That's everything I have to say. Thanks.